Hello everyone, welcome to this lecture in the Neural Networks from Scratch series. Today we have a very important topic to cover. We are going to be looking at learning rate decay today and why it is very important in neural network optimization. In the previous lecture, we looked at using a fixed step size in the gradient descent, and we saw that that eventually led to either of the two problems. If the step size was very large, we had these large number of oscillations back and forth and back and forth. But if the step size was too small, there was a high chance that we could get stuck in a local minima. I want to illustrate this with some video examples. So let me play this video here. In this video, the step size is very small. So here you can see that since the step size is small, we are getting stuck in this local minima here. We are not even exploring the entire loss landscape. In fact, at a much further point, there is an even better minima, which is much lower than the current local minima which we have found. However, because the step size is too small, we are getting stuck over here and we are not exploring this global minima over here. In fact, there are many points on the right hand side of where we are getting stuck where the loss is actually much lower. This is the biggest problem with a small step size. Second, if the step size is too large, then that has problems of its own. So, for example, here you can see that if the step size is very large, we just keep oscillating back and forth. The advantage of this is that we do explore areas where the loss is becoming very low. So, that is very good. The exploration here is very good, but we still don't land at this lowest loss because the step size is too large. So there are advantages and disadvantages with both the things. Ideally, when we are training a neural network, we should start with a high learning rate because we want to explore the entire loss landscape, right? So ideally, what should happen is when we start the learning, this is what should happen. When we start the learning, I want to explore the entire landscape, and it's fine if the learning rate is too large. But then what I want to do is that as I enter further and further into next iterations, such as what is happening right now, I know that I have kind of found this area where the minima is the lowest. So there, then the step size should be very small. So this is kind of like an exploration exploitation strategy. Exploration is the initial part where the step size needs to be very large, and exploitation means that once we have kind of explored all areas of the lost landscape, then the step size should be very small so that we can converge on the global minima, which is over here. This is the main idea behind the concept of learning rate decay. So, the main idea behind learning rate decay is this exploration exploitation thing which I talked about. So, exploration means that starting when you start the training, you start out with a high step size, but then as you proceed with the training and as the number of iterations increase, you enter into exploitation mode, which is basically you start reducing the step size now so that you can reach the global minima without bouncing back and forth. So this exploration exploitation is actually written in terms of a mathematical formula in which we have two things. So we have the decay parameter, and the second thing is the iteration number. The reason why the iteration number is in the denominator is that as I increase the number of iterations, I want the step size to go on decreasing. So if you plot this as a function of time, you will see that at time equal to 0, the step size starts at alpha naught and then it goes on actually decreasing with time. So this part in here is the exploration part, and this part here as we go further down is the exploitation part. Now in the numerator we have alpha naught. So at t equal to 0, alpha equal to alpha naught. So we start with the initial step size, and then as t proceeds further our step size goes on decreasing. So there is one more factor here which governs actually how fast our step size decreases. We don't want our step size to decrease very fast. because if the step size decreases very fast, what will happen is that the learning rate will be very small, very early, so we might get stuck in local minima. So this decay, the decay parameter or the learning rate decay, as it is called, controls how fast the step size is decreasing, and we don't want it to be very fast. So generally, for all practical purposes, the learning rate decay is kept around 0.001, which is 10 raised to minus 3. Okay, so this is the formula for the step size which we are going to be using. I just want to give you an intuition for how the step size decreases for different values of alpha naught, decay, and the time. So let's say we start out with an alpha naught equal to 1, and let's say we use the decay parameter of 0.1. So as you can see, I have shown you the values of alpha for 10 different time iterations, and you can see that alpha starts with 1.9.83, and within 10 iterations the value of alpha has actually decreased by 50%. For some problems this decay rate may work, but it's very fast. In 10 iterations we do not want alpha to decrease by half. And the reason is because the decay has been set to zero point 0.1. So the reason I showed you this numbers is for you to get an understanding of, if the decay is zero point 0.1, how fast the learning rate changes. Okay, so we are at this stage where hopefully you have understood the reasoning why we need to decay the learning rate. And now we are going to be jumping into code, and we are going to be looking at this problem which we have traditionally considered in this neural networks from scratch series. This is a classification problem. So the input data has two attributes, x1, which has been shown on the x-axis, and x2, which has been shown on y-axis. So any point which you take will have, it can be represented as x1 comma x2. That's the input data. And along with the input data, every input data belongs to either of these three classes. It belongs to the red class, the green class, or the blue class. Our goal is to train a neural network which looks something like this. This is just for representation. Our goal is to train a neural network so that given any new point, the neural network should correctly classify that point as belonging to red class, the blue class, or the green class. To do this classification, we will need to optimize the weights and biases of this neural network. So we will be doing this update procedure. In the last lecture, we looked at a simple update procedure like this, where the weights were updated and the learning rate was constant. Similarly, the bias was updated using the gradient descent rule, and the learning rate was constant. Now, what I'm going to show you is that instead of this alpha, we are going to be updating the weights and the biases with the decaying learning rate. And let's compare the performance of the pure gradient descent or vanilla gradient descent with a fixed step size versus using a learning rate. So I'm going to be jumping into code right now. Great. So we are going to be looking at the learning rate decay optimizer. In the last lecture, we defined the optimizer SGD class, where the only method was update params. What this method did was that it took layer as an argument, and then it uh, updated the weights and biases in that layer according to the partial derivatives of the loss with respect to the weights and biases which were returned by that layer. Remember, whenever a layer class is created, it has a forward method and a backward method. So we have stored the partial derivative of loss with respect to the weights and biases of that layer through the backward method. We are just accessing those partial derivatives through layer.d weights and layer.d biases, and then we perform the update rule. When we look at the learning rate decay, we will be introducing one more parameter here. So in the without the learning rate decay, when the optimizer was initialized, we just had the learning rate as the parameter, but now there is also the decay parameter whose by default value is set to 0. And then one more thing which we'll be doing is that in this init constructor, we'll be tracking two things. We'll be tracking the current learning rate, and we will also be tracking the iterations, because the learning rate depends on both these things. It depends on the current learning rate and the iterations. We'll be tracking the uh, initial learning rate as well. Okay. So now what we will be doing is that before any parameter is updated, we will call this function once, which is pre-update params. So that will set the current learning rate to this formula over here. And then what we will be doing is that we will be updating the weights and the biases. So this update params was there in the previous class also, where the learning rate decay was not used. In this method, what we do is that we just use the current learning rate and then update the weights and the biases accordingly. And note that the current learning rate is set by this formula. So this is alpha divided by 1 plus decay into t iterations. This is exactly the formula which we had seen here. The initial alpha divided by 1 plus decay into t. And then what we are doing here is that after the parameter actually updates, we are increasing the number of iterations by 1. So then the iterations will change every time, and then through that the current learning rate will be changing at every single iteration. So as the iterations proceed, we will be changing the learning rate through this pre-update params function, and then with the current learning rate we'll be updating the weights and the biases, and then we'll be of course increasing the iteration count after every iteration has been done. So this is the new optimizer class which we have, which includes the decay rate. And then the forward pass and the backward pass remain similar to what we had seen earlier. So in the forward pass, what we do is first we define the spiral data, which has 100 samples and 3 classes. Um, so this is the spiral data which we have introduced over here. This is the spiral data. We have 100 data points and we have 3 classes: red, green, or blue. We define the first layer which has 2 inputs and 64 hidden units, that is chained to the ReLU activation. Then we define the second layer which has 64 input units and 3 outputs. So these are the final output values which are then passed through the softmax activation and the categorical cross entropy loss. So this is the forward pass, or rather we are creating the instance of the class here, and then we'll be calling the forward method on all of these classes. uh, Before calling the forward and the backward method, first we will be defining the optimizer, and here we are going to be setting the decay rate to 0.001. Remember, this decay rate is generally good because we don't want a much larger decay rate. That would make the learning rate too small initially, and we might get stuck in a local minima. So we are going to be running 10,000 iterations. First, I am going to be running the forward pass through the first layer. I'll chain it to the ReLU activation. The output of the ReLU activation will be going to the second layer, and then I'll calculate the softmax output and the cross entropy loss. In this portion of the code, we are just printing out the accuracy, the loss, and the current learning rate at every epoch. Remember, one epoch means going through the entire data set once. And then we are of course going to be doing the backward pass, because we need to update the weights and the biases of the layer. So we are going to call the loss activation backwards. We'll start from the backwards. So first we'll find the partial derivative of loss with respect to the softmax inputs. Then we'll go backwards, find the partial derivative of loss with respect to the weights and biases of the second layer. Then we'll find the partial derivative of loss with respect to the ReLU input, and then we'll find the partial derivative of the loss with respect to the weights and biases of the first layer. Once that is done, we call the optimizer.pre-update params, and then we will update the parameter values based on the current learning rate and based on the partial derivatives which have been computed over here. And then we call this optimizer.post-update params, because remember, we need to increase the iteration count every single time, because that's used in the calculation of the current learning rate. So now this entire code has been defined. So now I'm just going to run this piece of code right now, and we are going to be tracking the accuracy. So here let us look at the accuracy. So the epochs are increasing right now, and we can see that the accuracy is increasing to zero point 0.5, which is very good. And we are right now at 3000 epochs. The loss is decreasing slowly, which means that we are not getting stuck in a local minima. As you can clearly see, the loss is still continuing to decrease. Um, Even as we reach 6600 epochs, the loss values are decreasing, the accuracy values are increasing. In fact, the loss has almost become, it has become less than zero point 0.7 now. And we are still keeping on going down. So after 10,000 iteration, I get an accuracy value of 0.717 and I get a loss value of 0.653. Let's compare it with the accuracy value from without using the decay rate. So remember, currently with the decay rate, we got an accuracy of 0.717. And in without using the decay rate, after 10,000 epochs, the accuracy was 0.573. And here we are clearly getting stuck in a local minima because the loss is not continuously decreasing, as you can see. Uh, and the loss in the previous case was 0.768. But in this case, when we use the learning rate decay, the lowest value of the loss towards the end was 0.653. And here you can see how smoothly the loss has decreased, which is another indication that we don't have oscillations and neither we are getting stuck in a local minima. On the rightmost side, you can see that I've printed the learning rate. The learning rate starts out from 1, and as the learning rate decays, or as we move further and further into the iterations, the learning rate has now become zero point 0.1 at the end of 10,000 iterations. That's the advantage of using a learning rate decay. I want to show you this in terms of visual videos. So let us have a look. First, let us have a look at without using the learning rate decay. So here we can see that learning rate decay has not been used, and on the right hand side we can see that the loss and the accuracy values are being plotted. We can see that as we reach towards the end, the accuracy is going to around 0.55 or zero point 0.6, and the loss is stagnating. The performance on the data does not seem to be quite good because all of these points here, the prediction says that they should be in the red category, but the data actually shows that there are blue points and green points also here. So we are making a lot of mistakes. Even if you see here, actually, if you see in this part, the prediction says that there is all a green boundary, but there are red points also here, which means that all of these points are getting misclassified. Now let us look at the video with decay introduced. Okay, so I'm playing this video here right now, and here we can see that we have a decay rate of 1 into 10 raised to minus 3. And as the video is we can see that the accuracy is increasing to much higher value than it was before, and the loss is also decreasing very smoothly. So as we reach towards the end of this video, we can see that we are doing slightly better in terms of the comparison, because here, if you look at this top right region, and if you compare it to, so in the previous plot the top right region was all red, so all these points were misclassified. But in this plot the top right region has good segregation. So for example, here it's blue, and that's because these blue points need to be correctly classified. And then there is transition to a red background here because there are red points over here. Then there is again transition to blue background. So this actually seems to be doing a much better job at classifying the data than if we did not have a learning rate. So this is the real advantage. This is the real advantage of using a decaying learning rate, as what we have seen in today's lecture. What a decaying learning rate actually helps us to do is that it helps us prevent local minima, and it actually also helps us prevent uh, later oscillating with large step sizes. So it kind of solves the problem of having too low a step size and too high a step size. So we start the training process with a higher step size, so we can explore the entire loss landscape, and then we start reducing the step size as we are getting closer and closer to finding the global minima. This does not guarantee that we will always find the global minima, but as I just demonstrated to you, it is better. In many cases, it is better than just having a fixed step size. However, it turns out that this is not the best. There is one more method which is much better than this, and that is actually gradient descent with momentum. We'll be exploring this in the next lecture. Thank you so much, everyone, for listening to this lecture. I hope you learnt a lot. We will see you in the next lecture.